Recording in progress.
Okay. Couple of announcements. On Monday, no lecture at all. I'm not gonna be here. So don't show up on Monday. On Tuesday, if you have Bluffton Lab, which is Alex and you, yes, and Jeb. No lab in Bluffton. Then on Wednesday, we're gonna have a review and practice session in here. It's optional. And then Beaufort Lab, everybody else, that will meet as usual. Right. So we left off talking about reactions of esters. We did saponification. We did acid catalyzed hydrolysis, which is the reverse of the Fischer esterification. And we did aminolysis. There's two more that we need to talk about. Then we have two more functional groups and then done. So extraction is reduction of esters. So in the same way that we can reduce carboxylic acids, and we'll do amides the same way as well. Pretty much a large range of functional groups can be reduced with lithium aluminum hydride. And like with the carboxylic acid, this reduces all the way to the alcohol. Sodium borohydride is strong enough to reduce aldehydes and ketones, but not adequate for carboxylic acids and esters. So you need lithium aluminum hydride for that reaction. And like most of the functional groups that we've talked about, you can react them esters with Grignard reagents. And like acid chlorides, when they react with Grignard reagent, they have to add two equivalents of the Grignard reagent. So take our ester. We need excess, well, really just two equivalents, but in practice you add excess of Grignard reagent. And we get a tertiary alcohol where two of the substituents are this R double prime group, which was from the original Grignard. And the ester substituent on that, the substituent on the ester oxygen is gone from the molecule. It ends up turning into an alcohol, so it goes away. And as I mentioned, you can't just add one equivalent of the Grignard reagent. It has to be two. The reason for that, no test on this or anything, but the reason for that is when you do the first equivalent, the first Grignard reaction on an ester, you get a ketone. And ketones are more reactive for the Grignard reaction than esters. So once it starts doing a Grignard reaction, it has to completely saturate that carbon with the R double prime group from the Grignard. Okay, so that's the end of esters. Okay, so that's sort of the general form. An amide, the old people are coming. That's the general form for an amide, but that's only one of them. We can also have something like this, where one of the nitrogens has a non-hydrogen substituent on it. And then we can take it a step further and give the nitrogen to our groups, R prime, whatever. And yep. And so this is a primary amide, this is a secondary amide, and this is a tertiary amide. And the primary, secondary, and tertiary naming, if you don't want to memorize exactly what these structures look like, just look at the nitrogen atom. And so pretend that there wasn't a carbonyl there. This would be a primary amine without the carbonyl, secondary amine without the carbonyl, and so on. Fortunately, for synthesizing amides, we've already talked about all of the reactions, well, not all of the reactions, but all the ones I'll expect you to know for making amides. And the reason this is starting to happen, and these next two sections are smaller, is because we're going from the most reactive functional group, the acid halide, to the least reactive, and now we're almost to the end. And so these functional groups aren't super reactive, amides and nitriles, which we'll do next. And so all the ways to make them involve those previous functional groups that are more reactive, because generally we want to go from a more reactive functional group to a less reactive functional group. Okay, so reactions of amides. We're going to have two different kinds of hydrolysis reactions. Acid, and then base hydrolysis. So if we take an amide, and I'm just going to use a primary amide because they're the easiest to draw, but it works equally well for all three different kinds. And we treat this with acid. Here I'm specifying that it's hydrochloric acid, not because you have to use HCl, but we'll see in a moment. This gives us carboxylic acid. Generally, hydrolysis is going to give us a carboxylic acid throughout this chapter. And then as a side product, well, our nitrogen's gone. And the nitrogen ends up as ammonium, and then the salt, the anion from the acid. So if you're doing this in like an organic solvent, still have water around, but most of everything is in an organic solvent. Ammonium chloride probably is not soluble and it precipitates. Have you all seen that arrow like that before drawn? So if you see like a down arrow drawn right after some sort of compound, that means that as soon as the stuff is formed, it falls out of solution. The reason that's useful is that drives the reaction forward. And because the ammonium chloride is sitting there at the bottom of the flask, it's not really going to react and try and go the opposite direction. Because, a lot of these reactions that we're talking about are reversible. But so this one is not reversible. Once you hydrolyze the amide, it's gone. Yes.
So if the solid that was formed was like lighter than the fluid it was in, would it be an upward arrow or does it not matter?
I like that. No, but I like that. The upward arrow means a gas. Because it goes up.
Oh.
So you're kind of correct that if it goes upward, then you draw it, but generally speaking, for a solid, we draw it down. Yep. Okay, acid hydrolysis. And base hydrolysis is really the same thing. H3O plus. In this case, well, we're also going to make a carboxylic acid, and so we're going to treat it with sodium hydroxide. That'll give us the carboxylate salt, and then because of that, we need some. Jeez. We need some acid in order to regenerate the free carboxylic acid. Additionally, we need heat because this reaction just sort of sucks and it's slow. Assuming that's HCl. Sorry.
Wait, what are you saying? You said assuming it's H3O.
Well, so I previously I said, okay, ammonium chloride. Well, there wasn't any chloride in here to start with, but whatever this anion is going to depend on what the acid is that you use to work. But this reaction sucks anyway, so don't bother. Okay. I'm gonna have you guys come up with this one. All right. Here we go. What are we thinking?
OH?
No, actually. So this doesn't have any oxygen in it. So there's nowhere for oxygen to come from. What lithium aluminum hydride usually does is take carbon oxygen or other carbon heteroatom bonds and turn them into CH bonds. So in this case, we're going to get rid of the carbonyl and just leave an amine. Now that's a really useful reaction because amines, we'll talk about after, right before the final, but amines are really useful molecules. And so if we can take like a carboxylic acid type thing where we've got a lot of oxygen stuff going on, convert it to an amide based on, one of our bazillion different methods, and then reduce it with lithium aluminum hydride, we can get an amine, so. Kind of. Going through a wide range of different kinds of functional groups in a small number of reactions. Yeah, so. Oxygen is totally gone here.
So an NPH4 wouldn't work here either, right?
No, no, yeah. Okay, so that is all of the carbonyl based functional groups. Other than really obscure ones like xanthates and all that stuff. So, closely related, which is why we talk about it in this chapter, are nitriles. So we can draw it like this, where we really explicitly draw out the triple bond. Or we can just say RCN. So these are really organic cyanides. So like sodium cyanide is sodium CN. But because we have a covalent bond between the carbon and another carbon. As opposed to just a C minus, it's not nearly as toxic. The reason for that is it would be the lone pair, the free lone pair on that carbon in cyanide that your body thinks is oxygen, and then you die. Unfortunately, it does often require using cyanide in order to make it. So, synthesis. These are pretty easily made by an SN2 reaction. So we take an alkyl halide of some sort with a relatively unhindered carbon atom, and then we add cyanide. So usually sodium cyanide, potassium cyanide, whichever one you happen to have on hand in your collection of cyanides. And this is a nucleophile. We're just going to do an SN2. And we get that nitro, which is also like that. So when we talked about carboxylation of Grignard reagents, we added CO2 to the molecule, and that increased our carbon chain by 1. This is not too different in that we're taking a small inorganic molecule that contains carbon and adding it to our molecule. And so that increases our number of carbons by 1. In this case, I think it's even easier to miss than with carboxylation of Grignard reagents, because it's usually the carbon is usually drawn out as a C. Like you could write this like that, but I don't like it. Some people do it.
Well, you put that on your exam.
No,
If this-
but I will put the bottom 2 because Need to know those. So, well, the good thing about this is it makes it more obvious, right, when you're counting the number of carbons, you're just counting the number of junctions, and so, oh, there's a carbon there. But here, you have to be a little bit more aware of that, and that's gonna come in handy. And we can also make nitriles from amides, right? Amides are a nitrogen containing functional group, so I think that kind of seems like it would make sense. And this is kind of an oxidation type of reaction. Technically, we aren't increasing the number of heteroatom bonds to the carbon, but it feels like an oxidation to me at least. And we're actually going to bring back thionyl fluoride, which usually would be used to make an acid chloride from a carboxylic acid. But when we use it on an amide, this is going to convert that to nitrile. Now, our central carbon from the amide is now the carbon of the nitrile. So we have one method that gives us an extra carbon because we're bringing in the nitrile already formed as cyanide. But here we're converting the functional group into that C and triple bond, and so we're not adding anything to the carbon chain.
Not you guys.
Yes.
You like the other white face. It's kind of funny.
Sulfur dioxide and which is a gas. So there's an up arrow. Sulfur dioxide and HCl. With maybe some adjusted stoichiometry. Something like that. Which makes that a really unpleasant reaction to do because sulfur dioxide is nasty. Okay, reactions of nitriles. Okay, hydrolysis. So you might think, all right, well, we can probably take a nitrile, do a hydrolysis reaction, and turn it back into an amide. That would be cool, right? Because we can go back and forth between two functional groups at will. Fortunately, that is not possible. It's not possible in this course. If you read my dissertation, you'll see how you actually do. But you generally speaking, you can't do that. So take a nitrile, some acid and heat. Yeah, initially you do get the amide. But it doesn't stop there, it continues hydrolyzing. And when you hydrolyze an amide, you get a carboxylic acid.
Unless you read your dissertation.
unless you read my dissertation. And even then, the catalyst that you have to use to do it isn't that good, actually, but.
What would be the benefits of stopping there?
There's, well, amides are used for plastics, adhesives, all sorts of different stuff, drugs. No, like good drugs. I can't think of any like illegal drugs that have a really obvious amide functional group, although there's probably one somewhere. And then like, there's all these, you can make like a web of functional groups and have like arrows between them showing reactions going back and forth. And there's almost an arrow going in every possible direction from one functional group to another, sort of. This one doesn't really have a good one yet. Kind of does now. So hydrolysis of nitriles goes all the way to the carboxylic acid and does not stop at the amide. Would not be complete without talking about Grignard reagents, of course. But this is better news, actually. So Grignard reagents we think of as reacting with carbonyl groups like aldehydes and ketones. But because of the polarity of that bond, the carbon is electrophilic, and so it can react with Grignard reagents. And so if we're careful to use just one equivalent of Grignard reagent, we don't have the problem with, like with acid chlorides and with esters, where it just goes crazy and adds two different Grignard reagent groups. Here we just add one. And the product we get from that is a ketone. Maybe kind of an unexpected result from that. The process this reaction goes through is a little more complicated than a regular Grignard reaction because we have to replace the carbon nitrogen with a carbon oxygen in addition to adding the R group, but we're not going to discuss that in any detail. Now, of course, we know that Grignard reagents do react with ketones, and so if you want, and add an additional equivalent of Grignard reagent, or you could add an equivalent of a different Grignard reagent. And so now you can make a tertiary alcohol with 3 different groups on it just from a nitrile. Last but not least, reduction. When we reduce with lithium aluminum hydride, not sodium borohydride, we get a primary amine, just like we do when we reduce amides. really drawn up here, but like the hydrolysis reaction. I'm not gonna say cannot stop at amide because where this process goes from nitrile to amide, then immediately to carboxylic acid, this one doesn't go through the amide in the middle, so cannot make. Amide this way. If you want to make an amide from a nitrile, at least with our chemistry, you're kind of screwed. Okay, that's it, the end. So I posted the problem set. There's, let's see, 1, 2, 3 of the first part. So the first part is predicting the product. The second part is filling in missing reagents above and below the reaction arrow. The third part is fill in the missing starting material. And then the last bit is kind of a more synthesis-like thing where I'm going to give you a chain of reactions and you have to fill in sort of the blanks. Kind of, it's just a more extended version of the other questions. Anyone that's looking at it, do you have one that you want to do?
Can we start A of question 1?
Okay. Ooh, yes. I like this one. Okay, so. This one is. See, and we're doing acid and methanol. Okay. What functional group do we have here? It's drawn upside down and backwards, but there isn't a such thing as upside down and backwards in chemistry. It'd be an aldehyde if we had a hydrogen here. Oh, there's a nitrogen. Yeah, left and right doesn't matter. So another way we could write this is. What, I heard amide? Yes. Oh, is it? Yeah, so this is an amide. So when you've got multiple steps like this, you want to make sure that you look at them individually, because you look at this and you say, okay, acid and methanol, what does acid and methanol do? Well, hang on, stop, ignore part 2, because that's later. Live in the present. Okay, so what happens when we treat an amide with, is it still here? Yes, it is. What happens when we treat an amide with acid? Well, that's gonna be a hydrolysis reaction. And we go from amide to carboxylic acid. The hydrogens, the substituents on the nitrogen, are gonna go away. So there's our nitrogen with its two substituents. So the nitrogen here becomes an OH. Like that. Okay. That was the first step, so this is. Amide hydrolysis. Second step was methanol with heat. So, what happens when we treat a carboxylic acid with an alcohol? If you look back at reactions of carboxylic acids, one of them is one we did in lab. Yeah, ester, Fischer esterification. So we're going to replace the hydrogen on the acidic proton on the carboxylic acid with the R group on the alcohol, which is methyl. So we get a methyl group right there on the oxygen. How do we like that? Yeah. Yeah.
And then we would have. Forming.
Yes. Yes. Can we do 3D? 3D. D, okay. So we're looking for some molecule that after sodium hydroxide and acid gives us butyl alcohol. Okay. So we're using sodium hydroxide in this reaction. Most of the reactions in this chapter that involve sodium hydroxide are what kind of reaction? It's also a kind of reaction that often gives us carboxylic acids. Hydrolysis, yeah. So we've got a hydrolysis reaction. And we have two products from our hydrolysis reaction. So we've probably broken apart what kind of molecule that might have aspects of both of those.
We at least know the benzene ring.
Yeah, so it's kind of the hydrocarbon part of each of these functional groups is gonna stay the same. The chemistry we're gonna do or have done, whatever, has to do with the. I don't know,
Is it also another benzene attached to it or no? Like is it two?
no, because that, if you had two benzene rings, they would both be present in the product.
Oh, okay,
So-
so, okay.
So this is an ester hydrolysis. So what ester would hydrolyze to form those two compounds? It's just one molecule.
Oh wait, the.
So where's our ester group gonna be? Well, we've got our double bond oxygen, single bond to oxygen thing. That looks like the foundation of an ester, right? So let's draw. That. And then what group is gonna be on the other side of the oxygen? That wouldn't be an ester. That would just be this thing. So look at the ester hydrolysis reaction, you'll see that it makes these two products, where this one is R, and this one is a different R group, R primes.
I need the R.
So we need R prime, yeah, we need this terpene group thing. So if we go forward, we cut the molecule right there. And this becomes our carboxylic acid. And that becomes alcohol. Okay, so I know I just dumped this practice on you and said, well, pick something, we'll do it really fast. But no lecture on Monday, and then on Wednesday, if you want to come and like work through all that stuff, we'll do that then. And then this problem set will be due a week from today. Next Friday. That's when we start.
Is that the? Exam too? Where's that?
Yeah. No, we still have chapter 21 to go.
When did you get it?
Next Friday, so the first day we start the next year.